In this lesson we're going to look at simple voltaic cells. Now we can think of voltaic cells as being the opposite to what we've been looking at in electrolysis. So in the case of electrolysis, an electric current is used to generate a chemical change between electrodes and the electrolyte, while in a voltaic cell the chemical change between the electrodes and the electrolyte is used to generate electricity. So in our simple voltaic cell we always require two electrodes which are different. Okay, they are made typically from different metals, and an electrolyte. So in this case our electrolyte is going to be a weak acid, for example, or a diluted acid, and we've got two different electrodes. The more reactive metal is going to become the anode, and the less reactive metal is going to become the cathode. This is the anode and this is the cathode. And just to confuse you, this is going to be the opposite to what we've been looking at in electrolysis. So in the case of a voltaic cell, the anode is negative while the cathode is positive. Whereas you'll remember that in electrolysis the anode is always positive, whereas the cathode is always negative. Okay, so what's going to happen at the anode is the metal's going to lose electrons, and those electrons are going to be pushed around the circuit onto the cathode. So if we just write a generic metal here, we just call it M, that's going to lose an electron, forming an aqueous ion, which will go into solution, and it's going to lose an electron. So we can say that the metal is oxidized at the anode. Okay, so these ions are going to go into the solution. This electron is going to be pushed around the circuit. So we can say that the electrons in a voltaic cell are pushed from the more reactive anode to the less reactive cathode. Okay, so what's going to happen at the cathode? Well, these electrons are going to be received by aqueous hydrogen ions that are present in the solution. Each hydrogen ion is going to pick up an electron, form a hydrogen atom. That's going to double up to form a hydrogen molecule, which means that hydrogen gas will be liberated at our cathode. Okay, so we have hydrogen gas coming off. Okay, so we can write the electrode half equation for the cathode. The hydrogen ion picks up this electron to form hydrogen gas. Balance it. Let's just suppose that this electrode is zinc. So we're going to have zinc forms the zinc 2 plus ion plus 2 E minus, and if our dilute acid were H2SO4, then we have the zinc being oxidized into zinc 2 plus ions. Okay, so these aqueous zinc 2 plus ions will gather around the anode, and as a result they will repel the hydrogen ions towards the cathode. The hydrogen ions will acquire electrons to form hydrogen gas, and likewise if it's sulfuric acid, then the sulfate ions will be attracted towards the zinc 2 plus ions which are gathering at the anode. Okay, so while the current is being carried by electrons through the conductor, through the electrolyte is being carried by the hydrogen plus ions and the sulfate ions as they migrate towards either the cathode or the anode. So we can complete this by saying that in each voltaic cell a redox reaction is taking place. Okay, so in this case we've got the zinc being oxidized at the anode, while we've got the hydrogen plus ions being reduced at the cathode, and we can write the complete redox reaction for the cell. Okay, so we've got Zn plus 2H plus gives us Zn 2 plus plus H2. So for this particular cell this will be the redox reaction that is taking place. Now the size of the voltage that's generated in this simple cell will depend upon the reactivity of the metals that are immersed in the electrolyte. So we can predict this voltage by looking at the various electrode potentials for each metal in the reactivity series. Okay, so here are some metals from the reactivity series, and here are their electrode potentials. And you can see that the order of these electrode potentials follow the same order of the reactivity of the metals. So as we go down this list, their reactivity decreases, likewise their electrode potentials decrease. You'll notice that hydrogen has electrode potential of 0, and then below that they become positive. So their electrode potentials are becoming less and less negative. Okay, so if this electrode were copper, for example, and we wanted to predict the voltage produced by this simple cell, then we find the electrode potential for zinc and for copper. Then the voltage generated will be the difference between the electrode potentials for zinc and for copper. So if we have a zinc copper cell, then the voltage generated will be equal to minus 0.76 minus 0.34, which is minus 1.1 volts. Okay, so if I wanted to increase that potential difference, then I could use a more reactive metal such as magnesium rather than zinc. And conversely, if I chose, for example, zinc and iron, then I would expect a lower voltage to be generated because iron is higher up in the reactivity series than copper. In this case, the voltage would be minus 0.76 minus, and then minus 0.45, which would be equal to minus 0.31 volts. Now then, with regard to this simple voltaic cell, it does have some drawbacks. While it can produce a voltage, it isn't really able to produce a very large current. It's quite impractical, and we're going to have a look at the drawbacks with regard to this type of cell in the following lesson.